Okay, so last time we started chapter 17, which is on amino acids and polypeptides and all that side of life, and we were getting into what sort of structural changes occur in amino acids depending on pH. And that's important for when we start putting these things together and making polypeptides, which is pretty much what we're going to end with. I would hope that out of this, you guys at least have some idea of how to draw a simple, maybe di or tripeptide. I don't know about much longer than that, but if you can do it with 2 or 3, you can do it with 10 of them if you really had to. But what would be the point of spending all that time? And we ended talking about so the different ionization states. We set at a pH of 7. We are above the pKa of this carboxylic acid. So that's why this guy is deprotonated at pH 7. Likewise, at a pH of 7, we're below the pKa of this ammonium group. So that's why the amino group is protonated. And indeed, this zwitterionic form is typical for the pure amino acid in solid form and also aqueous solution. Now, does here as well addition of alkyl group decreases the acidity of a molecule? I would have to think a while to figure out what I purposely did put only an alkyl group on this. This is valine, by the way, in case you're curious. Like I said, you certainly don't need to memorize all 20 of them. If you were to memorize glycine, which is the only one that's not chiral, the side chain is hydrogen, I'm good with that. I don't see the need to go and memorize the others. I know some of the others. At one time, I knew all of them. But I know that valine is the one with an isopropyl group for the side chain. And here I'm also not specifying stereochemistry. I don't think I'm going to emphasize that really greatly with you guys, but I showed you how you can draw these with the correct stereochemistry. But as to the effect of an alkyl group, I think compared to glycine, they're going to be about the same. And we're going to get to that because really what we're talking about here is the pKa's of the ionizable groups. And we already did some examples last time of what happens when also the side chain is ionizable. If it has, let's say, a carboxylic acid group or another amino group like in lysine. So we showed how to handle that. At pH is equal to 1, well, now we're going to be below the pKa's of all of the ionizable groups, whether they're on the side chain or just the amino group and the carboxylic acid. So I would expect this would look very much like that, except that we'll have the free carboxylic acid. It won't be the carboxylate. It'll actually be protonated, CO2H. And yes, there are some occasional nasty questions. I'm sure that's a message. Will you provide a final review? I did. There's one online. I am going to try to do some review today since I know how much you guys want that, but I do need to get through some of the, I have to get through some more material today as well. So anyway, that's how the structure of valine would look at pH equals 1. What about pH equals 14? Oh, so like I was saying, there are occasional nasty questions on AL where they want you to do it at a pH of 10.5 or 4.3. I'm not really interested in that. The only 3 pHs that I'm interested in are 1, 7, and 14, because those 3 are absolutely clear. There's never any question about the state of any of the groups, whether the amino group here or the carboxylic acid group here, or any of the possible groups on the side chains. There's never any question whatsoever. Whoops, I sure screwed that up, didn't I? Do we have a homework assignment for Friday? I don't remember. If you do, it's probably, see, I tried to avoid having anything due on the day after Thanksgiving. If it is due on this Friday, then it may very well be not graded. Oh, we're actually done. Well, that's nice. Then I can get your OWL scores. Awesome. So at pH equals 14, of course, not only is the carboxylic acid deprotonated, but we have the free amine over here. The amine free base, as it's called. And You've probably heard that phrase in other contexts, but it's used here too. So, so that's what you would expect for something with a non-ionizable side chain. Now, the reason I brought up valine with its non-ionizable side chain is this gets into something that I at least want to mention. It's not something that I'm going to put 20 questions on in the final exam. You know, I think one might be plenty, if even that. But there's this idea of something called the isoelectric point, PI. And this is kind of an important idea, especially in kind of, let's say, biology or biochemistry class, because there's a lot of techniques that are used that take advantage of the isoelectric point and use pH as a result. But the definition of the isoelectric point, I've put it in the class notes. It's the pH at which the overall charge on any one molecule is 0. Or you could also look at it as the overall charge on all of the molecules in the sample is 0. So again, that's in the class notes, so that's why I'm not writing it down. What section is that in? Either 17.2 or 17.3, but I wrote it down in the class notes. So I've given you the definition in the class notes. Where this comes in is finding the isoelectric point for something like valine, where there's nothing ionizable on the side chain. It's like an alkyl group, or maybe like glycine with an H, or something like serine that has an OH group. And that does have an OH group with a proton on it, but that's not going to change in the range of pH 1 to 14. You need a much stronger base than hydroxide to pull the proton off of an OH group of an alcohol. So anytime that, that the side chain doesn't get involved with any of these ionization changes or these states of charge over here, calculating the isoelectric point is dirt simple. All you need to do is average the pKa's of the ammonium group and the carboxylic acid group. And again, the pKa of these ammonium groups, I don't know the exact number for valine, but I would guess it's round and about 9.5 or 10. That's pretty typical. You can see that when you look at the table in the book, which again, I do not want you to memorize all of these different exact pKa's. But it'd be great if you knew that these ammonium groups tend to be round and about 9.5 or 10. Likewise, these carboxylic acid groups tend to be roughly 2.5, thereabouts. I think you'll find they're all pretty close. You know, there might be one that's 2.3 and another that's 2.6. So, but I think you'll find they're all round and about 2.5. And so the isoelectric point, again, as long as the side chain is not ionizable, is very easy. It's just the average of those two values. 9.5 and 2.5 makes 12. 12 divided by 2 is 6. So for most of this type of amino acid, I think you'll find the isoelectric point is round and about 6.0 for amino acids that have non-ionizable side chains. Now, it's considerably more complicated when the side chain is ionizable. And I never learned how to calculate that, and I wouldn't expect you guys to be able to also. But when the side chain is non-ionizable, it's very easy. You just add up these two pKa values, which I would think to calculate an exact value, you would need to be given the exact value for the amino acid in question. But you just average them. You add them up and divide by 2, and that will be your isoelectric point. I should mention, by the way, this is another thing that that they don't emphasize quite as much as I would like. The isoelectric point is not a thing that only applies to amino acids and polypeptides. Not at all. You can apply the idea to pretty much anything, especially any zwitterion. Why can't we ionize all of the hydrogen atoms in the amine? Well, because then that would put multiple minus charges on the nitrogen, and we really want to avoid charges other than -1, 0, or +1. And indeed, even to pull off this proton, you're going to need to go a lot more alkaline than pH equals 14. That amine probably is a pKa of somewhere in the upper 30s. So you're something like 25 pKa units away in order to be able to do that. Now, the difference between the protonated form, the ammonium salt, these two species can exist in aqueous solutions, certainly. But anything more than that, even just to pull off this one proton, you would need some stupidly strong base, something like H- or something like that. And then the second proton you'll never get off at all. You're not going to get N2-, not with any of these main group elements, not in organic compounds like this. You really want your charges always to be 0, +1, or -1. That's kind of in general. I can't think of ever having seen an exception, at least so far. Good, so, but I wanted to point out that that calculation is very, very easy. There's nothing scary at all about that one. The other ones where the side chain is ionizable, that is kind of scary, but I don't even know how to do it myself. And if I don't know how to do it myself, how can I ask you to do it? So please don't tell me there's some professors who would. Now I'm not going to believe it. Okay, so I think that's all I really need to say about that. You'll also get to review some of the old reactions, since they will certainly apply to amino acids. So this also counts as final exam review here. One of the things you can do to an amino acid, for instance, let me just pick another one. Let's do phenylalanine. Since I want to have something with another group on it that's not going to interfere. So this is phenylalanine. PHE is the 3-letter code, and hilariously enough, the 1-letter code is F. So misspelled. But anyway, recall that you can acylate the amino group. This is another way to make amides, just like you can acylate an alcohol and make an ester. So if you were to treat this with, oh, I don't know, acetyl chloride, well, then I would expect you would get this amide. Kind of running out of room over here. Sorry, guys. CH3. And then our carbon over here. This will now go to CO2H because you're going to have a neutral molecule. And then this over here, because this nitrogen's not going to have a plus charge any longer. You cannot easily protonate amide nitrogens. That generally takes acids stronger than certainly in biological conditions. So since the nitrogen is neutral, that's how we also know that this group is also going to be neutral. But this is just acylation of an amine to make an amide. We talked about reactions like that in chapter 10. We also said that you could take acid chlorides or acid anhydrides and treat them with alcohols to make an ester. So this is just like that, except it's a nitrogen instead of an oxygen. So that's chapter 10. Let me see if I can, yeah, that's in 1021, but certainly it's in chapter 10. Another thing that we talked about in chapter 10 is Fischer esterification. And you certainly can do that to an amino acid. In fact, it's done all the time. It's a very common way of derivatizing it. So that if we were to treat phenylalanine with ethanol, just dissolve it up in ethanol and add an acid catalyst and heat it up, maybe add a few specks of sulfuric acid, anything that we can reasonably call H+. So again, this is also final exam review. This is from chapter 10. And then it will simply esterify the carboxylic acid. Can you add an acyl group to a carboxylic acid to make an ester? You can, but it's not as easy as this. And anyway, you won't get an ester. You'll see you get an anhydride, which is significantly harder to make. I certainly think this would react much more quickly with the nitrogen here. But just as before, this is now going to go back to being neutral, since we need a neutral product out at the end. And now instead of a carboxylic acid, we will have an ethyl ester, since I used ethanol. That's a very, very common way of derivatizing amino acids. So you would just get the ethyl ester, and that is in 10.9 to 10.10. That's where we talked about ways of making esters. This is just a Fischer esterification. So that will still work. So my only point here is there's some reactions we already learned for carboxylic acids and amines. They still apply here. Is this a reduction reaction? I think we had that question the other day, and it's a good question. And I gave the same answer then. The answer is no, this is neither oxidation nor reduction going here, because everything stays in the same oxidation state. These two oxygens here in the -2 oxidation state, there's still -2 here. So this is neither oxidation nor reduction. Likewise, the nitrogen is at -3 here, it's at -3 over here also. And there's certainly no redox to any of the carbons. So, so that's the best way that you can know if you're getting reduction or oxidation, is track changes in oxidation numbers, but I think you'll find there aren't any. So this reaction, both of these reactions are neither oxidation nor reduction. They're just substitution reactions, which generally are not redox. Good, so that was just a quick overview of some of the reactions we learned in other contexts that still work here. And really the only other thing, let me see, I really should mention disulfides, and then we'll end with how to draw a typical dipeptide, and at least in the simple form without worrying about stereochemistry. So one rather intriguing amino acid is called cysteine. And that one, what is the reason N does not react with alcohol here? I don't think we've ever seen a case where nitrogens react with alcohols. The way you know it won't react is that the oxygen is a nucleophilic atom and the nitrogen is also a nucleophilic atom. That's how you know it won't react. Nucleophiles don't react with each other. Electrophiles don't react with each other typically. At least that's what I would say. So that's how you know what to look at in terms of what atoms will react with which other ones. But also, here we go. So let me think now. At pH 7, yeah, we're fine. As I recall, the pKa of thiols is something like 10. So yeah, we're fine. This will still be protonated. So this one is cysteine, CYS. I think the one-letter code is C, but not really too important here. But this is important that it has the thiol or sulfhydryl functional group. You might recall from your even high school biology classes that we have these things called disulfide linkages or disulfide bridges. And what can happen is that the SH group, an SH group may be in one part of a long protein chain, and another one may be several hundred residues away. If they get close enough to each other, they can form what's known as a disulfide. And I think we've talked a little about this already, but it bears repeating. This is not just true for those sulfhydryl groups, but in general, you can treat 2 molecules of a thiol with some oxidizing agent. And recall that O in square brackets is like shorthand for oxidation is occurring. And in that case, you will get what's known as a disulfide, which looks like this. It's kind of the sulfur equivalent of a peroxide. So this is a disulfide. And the opposite's also true. You can reduce a disulfide back down to 2 thiol molecules. So H in square brackets is shorthand for a reduction is occurring. So here we do have redox happening. unless I'm losing it, which is always possible. I think here you have sulfur in the -2 oxidation state, and here it's -1. So we do have a change in oxidation number here. Now, why are disulfides important? Well, because they're going to affect protein structures. If you have these disulfide groups between otherwise distant amino acid residues, that's going to change how the protein chain folds around. And I mean, we're not going to get big into protein structure and function. I don't think it's appropriate in this class. But I think it's enough for you to be able to see that's going to affect the structure of the protein. And once you affect its structure, you affect what it does. You're talking about why enzymes will catalyze this reaction and not that one. As soon as you start mucking around with protein structure, you're also at the same time changing or affecting, I should say, the function of that protein molecule. O in square brackets is just a generic oxidation. It means oxidation is happening, but we're not specifying reagents. Though there are certainly biological oxidizing agents that you might have heard of. Things like NAD+, NADP+, FAD, those are biological oxidizing agents. And likewise, there are also biological reducing agents. This would be your NADH or your NADPH or FADH2. So this just means generic reduction is taking place. But these disulfide linkages greatly affect protein function. And one real-life example, though I said this just recently to a different class, one real-life example of where we mess around with these disulfide linkages is if any of you has ever gotten their hair permed. I don't know if people really do that still. That was really big in the 70s and 80s, and so I'm told, even into the 90s. I just wish I had enough hair left that I could get it permed if I wanted to, but unfortunately that's quite out of the question. So, but what happens when you get your hair permed is they first reduce all of these disulfide linkages in the proteins in your hair, then they move it around however they want it to be, and then they reoxidize it. They reform those disulfide linkages, and so it stays in that shape. So that's a real life example. That is if people still do that, which, like I said, I wouldn't know. I don't have anywhere near enough hair to get a perm if I even wanted one. But if you do, or if someone you know does, that's what's going on there. It's just redox chemistry. And so I think besides that, I think all we really need to consider is the structure of polypeptides, how it is that you put multiple amino acid molecules together to make a polypeptide. And the answer to that is it's always going to use amide functional groups. The thing that you might have heard of as being called a peptide bond is an amide. It is one and the same thing. So if you know what an amide is, then you understand everything you need to know in terms of how individual amino acid residues come together to make polypeptides. So just to recall, an amide functional group looks something like this. And the way we're going to make it is we're going to take the carboxylic acid carbonyl of one amino acid and attach it to the amino nitrogen of the next one. And so in order to get a dipeptide, that's what we're going to do. And in the process, we'll lose a molecule of water. Now, of course, there are enzymes that do that for us in living systems, because that's not a particularly favorable reaction. Carboxylic acids and amines do not react readily. In fact, if you didn't have an enzyme at all, I think we said this even, all that'll happen is the carboxylic acid will give up H+, the nitrogen will take it, and you'll just get a salt, and that will be the end. But I have an example here in the class notes. So since we certainly do have time, I have here, looks like serine and glutamic acid. Actually, I know what I'll do. Let's use some colors. So this is serine. As I recall, its one-letter code is just S. And let's make our glutamic acid a different color. And again, you can see I'm operating at pH 7. So glutamic acid is CH2, CO2H, or at pH 7, CO2 minus. This is glutamic acid. Double check me on this, but I think the one-letter code might be E. I don't care if you memorize them, but I do want to at least be correct. I'm like 90% sure it's E. So what if we wanted to put these together to make the dipeptide serine glutamine? Well, what we would do is we would start with the structure of serine. And you'll notice, by the way, by convention, we start at what's called the nitrogen terminal, the amino end of the molecule. That's commonplace. I think you'll find your biology and biochem professors doing pretty much the same. And everything else just goes along for the ride. And so now, instead of putting OH here, we're going to put this nitrogen atom. And of course, that nitrogen will no longer be protonated. You're not going to protonate amide functional groups. But the rest of it is exactly the same. And then CO2 minus over here. So this carboxylate group is the same as this carboxylate group. The other one is at the end of the glutamic acid side chain, or glutamate side chain. So I think it's worthwhile for you guys to know how you get from individual amino acids to polypeptides. And we could keep going. We could take a third amino acid and condense it with the carboxylate group over here, make another amide functional group, and then you get a third one. We could do the opposite. We could take this amine and find the carboxylate end of another amino acid, lose effectively a molecule of water, and have a third one over here. And we could go as far as we like in both directions that way. But I do want you guys to be aware, I think I would be remiss in my duties if I didn't make it clear that what we normally call a peptide bond is an amide functional group. They are one and the same thing. And with that, yeah, I mean, I think that's the basics. That leaves us at 330, meaning we have, what do you mean is there diamide? Can you have two consecutive amides, like one right after the other? No, the way you know that is because once you have this nitrogen here, there's not going to be a carboxylic acid on the other side. You're going to have the rest of that molecule, of that of that amino acid molecule. And then we have a carboxylate terminal over here, and we can make another amide there using the nitrogen now from another one. So the product is this. This is the product. That's how you would write that. It's a dipeptide, meaning two amino acids hooked up together in order to, well, two amino acids hooked up together. But this part is invariant. That amide functional group always goes in between any two adjacent amino acids. Always, 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 always. No exceptions. So, I mean, if you want to see what yet a third one would look like, I could show you. If we did serine and glutamine, then, oh, let's make it easy on ourselves, glycine. Would not be too complicated. We would use this carboxylic acid functional group over here. And that's going to then go to the nitrogen of the next one. Kind of running out of room over here. And then CH2, because it's glycine, and then CO2 minus. And we could, if we wanted to, do the same thing again with the fourth one. If we wanted to put another amino acid over here, we could, but this would be an example of a tripeptide. Let me do it this way. Let me give you a visual aid as to what parts of the molecule go where. That's the serine. The glutamate portion is over here. And then this part will even get a new color. This part over here, the part that corresponds to glycine, is all the rest of it, all of this stuff. But I think you can see there's a repeating pattern, and you're always going to get an amide functional group in between any two amino acid residues. And then I think is really one of the main points of this chapter, is understanding how you put together multiple amino acids in order to get a polypeptide. But again, at this point, having learned all we have about the functional groups, I do not think that's beyond the realm of understanding for us. I think that's something we can grasp rather easily. But imagine doing that several thousands or tens of thousands of times, and you've got yourself a protein. But at bottom, the protein structure is exactly the same as this, at least in terms of what they call the primary structure, meaning the order of the amino acids. At bottom, there's going to be an amide functional group between any two adjacent amino acids. That part's invariant. That will always be that way. Good, and I don't really want to burden you with anything else in terms of that chapter. That at least is all that I was going to talk about. That leaves us time to do our reef questions, and if we have some time after that, I can do some review for the final exam. Although I don't think I'm going to be able to make anyone happy, or at least not very many of you happy. I'm not going to be able to do much about, I'm not going to be able to satisfy everyone's curiosity about every subject, but that's okay. We can at least do something. Okay, so please register your attendance, of course. That's 8 out of the 10 points today. Oh, right, I need to do slideshow from beginning. Someone says their reef isn't working, can't be helped. Remember, that's why I drop at least 30% of them. Everyone has errors with reefs sometimes. It's also why I'm seriously considering just doing attendance next term. If that discourages people from coming to class, well, anyone who takes a class like this and doesn't come to class, you're out of your mind. That's how I consider it anyway. So it should still have registered your attendance at the very least, but this is why I drop at least 30% of them. All right, 10 more seconds. Not a trick question, hopefully something fairly straightforward. Going. Anyone else? Yeah, that's what I expected. I think a lot of people came in, registered their attendance, and then left, which it's not my problem. Anyway, we just talked about this. I'm hoping everyone put E for amide, because a peptide bond is an amide group, period, full stop. So I think E is the best answer, as did you guys. And last but not least, there's a particularly goofy amino acid. The structure of proline is given below at pH 7. What is its total charge at pH 1? I could totally have put that on the final exam. I'll even give you guys a little hint. Let's figure out what its total charge is now at pH 7. I see +1 and I see -1. So I think at pH 7, the total charge is 0. So what would the total charge be at pH 1? All right, looks like that's it. So when we go down to pH 1, remember the lower the pH, the more acidic, right? The lower the pH, the more acidic. So when we go down to pH 1, we're below even the pKa's of these carboxylic acids. So I think that's going to be the only change. We'll go from CO2 minus to CO2H, and that will leave just the +1 charge on the nitrogen. So I think the best answer is D. I think the charge will be +1. Let's see what you thought. You agreed with me. That's great. That means either we're all right or we're all wrong. Again, how? I'll show you how you can know that. So you need to know that at pH 1, the carboxylic acid group is going to be protonated. It's instead of O minus, it's going to be OH here. That gets rid of this minus charge. Now that nitrogen, that oxygen rather, is neutral. Meanwhile, that nitrogen is going to stay the same way. You can't put another proton on. It would have 10 electrons around it. So if you go from O minus to OH, that makes the total charge +1. Working on it, goodness. Okay, so we do still have a few minutes. Since I know you guys want me to review, I'll try my best to give you something that you can use. So anyone remember way back in chapter 4, or was it 5? I think it was 4. Yes, that we discussed the reactions of benzene. And we just did a quick trip through it. We didn't get into any great details, but we said that benzene is first of all not an alkene. And second of all, unlike alkenes, which undergo addition reactions, benzene likes to undergo substitution reactions. And we learned such reactions as benzene reacts with bromine in the presence of either aluminum bromide. So let me write chapter 4. So phenol doesn't react with what molecules? Phenol will react with any of them, any of the same things. But what we didn't learn is, oh, sorry. Oh, it's not working. I don't know why it's not working. Well, that's strange. Somehow it thinks I have a second monitor. Well, here's what I'll do. I need to finish writing the structure of the product. So, for instance, if you reacted benzene with bromine, I don't know of any other way to do it than this. There, now you at least can see it. So that's one of the electrophilic aromatic substitution reactions we covered. We covered about if I live through it, that is. Let me now add something else to this. You were asking about phenol. Well, I didn't want you guys to have to learn about directing groups. So what I'm doing here is I'm rewriting bromine and aluminum bromide, or you can use iron 3 bromide also. And I know I gave at least one question like this on that exam, where I said, what would the starting material have had to be? Is phenol an electrophile? Well, it depends on, oh, wait a minute, I think I see what might be the problem. No, that didn't solve the problem. In this type of reaction, phenol can be an electrophile, but the problem is phenol already has a pre-existing group on it. It has that OH group there. So I didn't want you guys, and I still don't expect you guys to learn about directing groups. But I know I asked a question that was like this, which was, what must the starting material have been? And what I would expect you to do in this case, what you need to know is you need to look at that and say, well, I've replaced a hydrogen with a bromine, because that is what always happens, without exception, when I treat an aromatic compound with bromine in the presence of aluminum bromide or iron 3 bromide. Now over here, that means that I must have replaced this hydrogen with a bromine, which means that the OH group was there first. So that means my starting material must have been phenol. Oh, you see, the trouble is over here, half of you can see it, and the people that are in person can't. Can you see it? Can you see it now? Wait a minute. Let me see if this will fix it. Let's just start over. There. It's not here in the classroom either. Well, I don't know what just happened, but now when I do this, what I'm doing, basically the thing thinks that I have another monitor. Oh, can you see it over here in chat? Because this way the people in class can't see it. Well, if you can see that, then what I'll do is I'll write down the answer. But basically, I know I asked you a question like, if this is the product, what must the starting material have been? And so the starting material must be benzene with that OH group already in place. In this particular case, phenol. Now, what this is telling us is with the OH group here, the new group that's coming in, which is a bromine, will wind up para. This tells us that OH is a para-directing group. Now, I don't expect you to know that. I know it. But you see, you don't have to know it to get a question like this right. All you need to know is that this is an electrophilic aromatic bromination, and so that means this must have been the starting material. So now let me put that up so that the people in the classroom can see it. I don't know why it's wanting to do this all of a sudden, but I'll leave that up there for a little bit. Other than that, I'm more than out of time, but it's been a pleasure this term. I've learned a lot. I've learned about face shields and mics and all this stuff. Next term, it looks, which doesn't affect you so much, but next term it looks like we're going to strictly online. So I think the powers that be have decided that this mixed format isn't the greatest. But it's been a right pleasure. Oh, I know what I should tell you. I will be having office hours tomorrow. Not on Thursday, of course, that's Thanksgiving. I'm planning to come in at least on Saturday and quite likely the following Tuesday after that as well. I mean, it's not like I'm not going to be there. I would be lying if I said that I couldn't do it. So, but certainly for sure, Tuesday and Saturday, I'm doing office hours. So other than that, best of luck in the final. You guys will be fine. You'll be fine. Anyway, maybe I'll see some of, I guess I'll see all of you on screen at least at some point before the term's all over. See you all later.